So so you do have professionals involved in this too, but the spirit of it, it sounds to me like, is you want to get a network of people around the world, both professional and amateurs, to contribute data to measuring habitable exoplanets, right?
Exactly. Yeah. The idea is actually the idea is very simple. It's just as you said, several observatories monitoring, well, gathering data from one store at the same time during several months. That's basically the idea. Well, first of all, we thought about monitoring several stores at the same time. But well, when we started doing doing it, we realized that one star at a time was enough. So
Yeah.
yeah, we are monitoring one star several months, several observatories
Okay.
at different times, of course. But our idea is to cover the star 24/7, the whole week. Right now we are only at 80%. We only cover the week 80% of the time. So we still need 20% to reach that full 24/7. So that's why we're looking for more observatories. Yes.
And so the idea is to be 24/7 somewhere in the globe. Somebody is measuring a habitable exoplanet star somewhere. And do you have you have a very specific list of those stars, right? How many stars do you have?
Exactly. We found around 10 stars. Well, it's not a definitive list. I mean, of course, there are probably more stars, but by looking at the NASA database on exoplanets, we found 10 stars that are they are located within 100 light years. They have they have exoplanets around them that were found using the transit photometry method, but none of them have habitable exoplanets. So we thought that it was a good idea to just focus on those stars that already have exoplanets that are in our line of sight, which are a very small number of stars that are available for discovery of exoplanets. Most of them are only able. I mean, it's only able to, as far as I'm concerned, it's only able to find exoplanets with the radial velocity method or other methods. But for transit photometry, it's really a small percentage of stars. So yeah, we only found those 10 stars. They are non-flare, of course. We focused on non-flare stars without flares.
You focus
And
on
only,
non-flare stars,
yeah,
stars
and
that do
only,
not flare, because the photometry is so precise that you can't have variable. You can't be able to expect people to take out the variability of the star as well.
yeah, I mean, of course. I mean, and also we thought about the habitability component. Of course, there are stars like Proxima Centauri, which currently we think that there is a potentially habitable exoplanet, but we are really confused because for at least for me, it's really difficult to believe how a habitable exoplanet can orbit a star with such flares. But we prefer to remove those flare stars in order to be more to focus on the habitability component. And also GK or M type, we removed all the other stars from the list.
Okay, so these are stars that, first of all, NASA or somebody has to catalog them as habitable, and these are planets that are with that. Whatever you might think of the current definition, folks, it is what it is. This is a place where they're a habitable planet, roughly Earth-sized, rocky, and can be in. It's at a distance from its star where liquid water could be present if it had any. And so this is what we're currently calling a habitable exoplanet. And so it has to be cataloged as one of those. It also has to be non-flare, as you say, and then because it flaring stars are hard to live around, I suppose, but they can be. And they are also these stars that you've selected also have to be relatively close by, don't they? Or they at least have to be bright enough so that you can get the photometry that you need in a variety of telescopes, right?
Yes, exactly. We focused on stars only within 100 light years, and actually, yeah, it's difficult. I mean, the smaller the star, the bigger the aperture we need. So our most of the observatories involved have like half meter telescopes, 300 centimeters. Well, I'm not sure in inches. How would it be? 16 inches, something like that. No, so yes, I mean we have like there's a limit there in the type of star we can monitor. Uh, for example, the one we started monitoring is Gliese 436, and I'm not sure how it's like 12 or something like that, the magnitude of the star. So of course we cannot, for example, monitor stars like TRAPPIST with a magnitude of visual magnitude, apparent magnitude of almost 20. That would be impossible for the equipment that we have. So yeah, maximum 15 more or less, the magnitude of the star.
Okay, so okay, good. So magnitude of about 15 or so. Now I've put up this light curve of KOI 2626 that you sent me, and this is an example of the kind of data that you're getting from your network.
No. That's the light. Do you mean the light curve of Kepler 1652b,
Oh,
or
oh no,
which light?
you sent me one that says KOI 2626.01. That's what I have.
All right. Yeah. Yeah. Sorry. Yeah. Sorry. That's the. I think that's the other name for Kepler. Yeah. Sorry. Different names for the same star. But yeah, that's
Yeah. KOI
exactly.
stands for Kepler Object of Interest, by the way, and
Yeah.
I think these are unconfirmed, but I can't remember either. The nomenclature changes to the point where
Yeah. I
I
think
don't remember it either. But okay, so is this an example? This light curve that I'm showing now, is this
yeah.
an
Well,
example of of what you're able to do, or is this some other from a professional observatory?
yeah, well, I took this graph from the paper, from the publication of. I mean, this is a real potentially habitable exoplanet.
Okay,
But
all
yeah,
right.
we are searching for something similar to this because Kepler. I mean, I thought that it was a good idea maybe to find some kind of example. So the observatories know more or less if they find something, they more or less can know what is it. No,
Okay,
so
so
yeah, this one
you
for
picked
example.
that as an example,
As an example,
habitable
yeah,
exoplanet that you want to follow up on with other observations.
exactly,
Okay,
because
all right.
Kepler was 162 has a similar mass and similar mass and diameter to Gliese 436. They are very similar. So so yeah, I mean the semi major axis length is similar as well, and yeah, doing the calculations, we arrived to the conclusion that the depth of a habitable exoplanet will be similar to one around Gliese 436. Also, the duration and the orbital period.
Okay, all right. So good. And so let's get back to the so this is what you're trying to do, and obviously you're trying to do this with the transit method. And for those of you who are watching for the first time, the transit method is with the dip in brightness of a star that is due to a planet passing between us and that star. And this has become something that a lot of people can do now, not just professional observatories. It used to require very high precision photometry. Well, it still does require it, but that kind of precision was only in the hands of professionals at the time. But it's always been done with smaller telescopes. I mean, I've told you this story many times about a guy named Tim Brown who worked at the High Altitude Observatory who set up a f 2.3 telescope using on a Meade LX 200 mount in a parking lot of the observatory, and he started taking some of the very first light curves ever. His graduate student, by the way, David Charbonneau, who went on to become one of the foremost leaders in the field. So this has been done for a long time, since the late 90s, and it's been done with modest equipment. The problem has always been photometry accuracy and the processing of the data. And things like cameras and processing software have gotten to the point where a lot of us can do it now. And so what Alberto is setting up, and I think is very exciting, is he's going out with a very well-defined list of stars that they want to do follow-up observations on, because professional observatories can't do this, not long term. And what we want is many, 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 many data points, as many as we can possibly get, because we don't always look at the star when the planet is passing right in front. Sometimes, imagine a planet like Jupiter. I know it's not habitable, but imagine a planet like Jupiter. It takes several hundred years to go around its star. Well, it's going to be a while to see it. We need to keep looking at it all the time to get a complete data set. And that's what programs like this do. And the reason that this project is striving to go 24/7 all the time, no matter where you are in the globe, somebody is observing this star, is because you don't want to miss anything. You can get high frequency planets this way, and lots of other really cool things. So I really think this kind of thing is really important. So Alberto, now I also should mention, because I didn't at the top of the Hangout, there's a link to their website down in the description box. There's also an introductory video that I posted a link to as well. Go watch that, not now, but go watch that and reach out and interact with these guys. So Alberto, let's say I learned about this. I've got a telescope. I've got a I don't know, let's say a 10-inch Dob or whatever I've got, and I've got some camera equipment. How do you evaluate and get new members of your network? What does one do to get involved?
Well, first at the beginning, I contacted to there is in the Czech Republic there is an astronomy association. It's called their website is called the Exoplanet Transit Database. They have a network. They already have a network of like I don't know how many, like 200 observatories, amateur observatories, and they are located all around the world. So it's very easy, because what I had to do is just send them an email. I sent them an email asking them whether or not they wanted to be involved. Yes, some of them wanted to be involved. Most of them were already, doing. They were already in this business. They were already. Some of them are in the TESS follow-up program. They are ready. They are trying to confirm exoplanets already discovered by TESS. So yeah, more or less, most of them already were in this field of amateur research. So for me, I just sent them an email, also to the American Astronomy Variable Association, Variable Star Association.
Yep.
Many of the observatories come from there as well. So a little bit of the two associations, astronomy associations. Yeah, that's actually there, because I'm not. I don't attend any observatory by myself. So I did all of these online, without not personally.
Okay, but I still don't understand. So how can you get involved? Do you like send people? First of all, can anybody get involved?
Yes, well, the only requirement, the aperture, the telescope, someone needs to have a telescope, of course. The telescope, the aperture, the minimum aperture of the telescope would be maybe 8 inches, something like that, 200 centimeters, more or less. Of course, the mount has to be good for astrophotography. The camera is in my opinion, the camera is the most important component, because, for example, the satellite doesn't use big apertures, but the camera we need is, in our case, it has to have at least a resolution of at least 16 bits of resolution. So
I'm sorry, a resolution of what?
16 bits. That would be
16 bits per pixel. Okay, sure.
Exactly. The bit rate. That would be more or less the resolution we need. So, for example, I have a camera set.
Well, that's not a resolution so much as a bit depth. And so, but I see what you mean. You need each pixel to have 64,600 and whatever it is values to it. Which brings me to this question. So I get in contact. Do I get in contact with you, or do I just submit a form through the website?
Yeah, that's the best way, I think.
Okay.
Submitting a form through the website. But yeah, so far almost nobody has done that. Just one
Well,
of the
that's what we're
observatory.
hoping to change by doing this hangout. We want people to
Yeah, yeah,
contact you. So if I've got a C8 or something, an 8-inch telescope with a halfway decent camera, 16 bits isn't much, and I could contact you and say I have this following setup. I'd like to get involved, and then you would presumably email them back and tell them what observations you need. Is that right? And then what?
yes, exactly. I just need the location of the observatory, and well, I have like an schedule, the one I sent to you before with all the hours and the. So yeah, it's
I
like
have it up
normal.
now. By the way, it's being shown. The schedule that you sent me is up.
Oh,
So
all right.
you what we have is a UTC time where of the things of who is observed. I see a lot of observatories,
Mhm.
and this is showing who is observing at a given
Yes,
time.
yes, it's more or less it's organized that way. Yeah. So I ask the observatory, what time would you be able to observe? And they tell me, oh, I can observe this amount of time. Well, there is a requirement. Let's say of at least 4 hours of observation. My initial idea was to do 1 hour. I mean, each observatory 1 hour, but that would require like I don't know 200 observatories. Also, it would be really difficult to combine all that data to finally see a potential liker. So I thought it's better. Well, most of the observatories that were getting involved decided to actually they were able to conduct hours sessions of 4 hours or even 5 and 6. So I realized, okay, that's the best way. Each observatory makes observations of 4 hours, 5 hours, something like that. So this would imply less a small number of observatories compared to just 1 hour.
Okay,
So
but the
yeah, more
idea
or
is
less.
when you are observing, you want to get through as many of these stars as you possibly can.
Sorry.
So while you are observing, though, let's say you're on this schedule to observe, you want them to get through as many of the stars as is visible to them, correct?
Yes, yes,
Okay.
yes. Well, the idea is to observe the same star, all of them the same star. But yeah, that's the idea. So yeah, it's kind of difficult because well, there have been many problems. I mean, some of them have bad weather sometimes. Uh, Especially those in California, they have had bad weather recently. I mean, so and yeah, and there have been some technical problems as well. But I guess this happens to everybody. I mean, to any type, even the professional observatories. Well, not about the weather because they are located very high. That's one of the inconvenience of this project that the observatories are not located in high mountains. They are like sea level, most of them. So yeah, the weather is a problem sometimes.
Right.
I try to find most of I try to find observatories with good weather. If you see the list, you will realize that all of them are located, in Arizona and south of Spain. All of them, I didn't found I didn't look for any observatory in England or something like that. No? So the weather was a really important key.
Okay. Um, I guess so. I'm trying to outline the method that a person listening to this might follow to get involved, and so that's why I keep coming back to this. So they reach out on your website. We've told them the kind of equipment you're hoping that they have, something on the order of an 8-inch telescope with a camera that is halfway decent, 16-bit camera, which is most of the cameras now. That's minimum, and then they will get on the schedule that we just posted for observing. Then obviously it depends on the weather what you can take. So now I've done this. I've gotten my first night's worth of observing on some stars. I've got some light curves. I've got some data points. Are you going to take this data or do I and then do stuff with it, or am I going to have to process it at home before I send you any data?
Yes, well, we give the two possibilities. But most of the observatories are processing the data by themselves. So they are actually they are using most of them Astroimage data, the software, and they are analyzing the data by themselves and doing the light curves. So I don't have to do it by myself. except for one observatory, the Chinese one, they weren't able to do it. So they sent me the data, and I processed. I mean, I did the photometry. But yeah, they have the option to either upload. Well, in the website we have like a forum. The observatories involved just register in the website, and they have access to all the data. The data, they have like a sort of they have a box where they can upload their own data and the light curves. So yeah, they can either provide raw data, just the feed files, or they can also provide photometry data and also the light curves. A screenshot, for example, of the light curve, something like that. But yeah, it requires. I mean, it doesn't require the person to be they don't have to know how to use a StreamXJ. I can do it by myself. I only need the raw data.
Because I think that's important, Alberto. If you had, first of all, everybody's got different systems, and so calibrating is huge. It's a huge problem, and so I get that everybody needs to take their own darks, flats, and biases and do those kinds of subtractions and corrections locally. That's something almost every piece of software can do automatically now. But then doing the photometry itself from an image can be wildly different depending on how you use it. For example, if you use DS9, which is a popular program for professionals, then that you would use aperture photometry, and how the size of the aperture matters, and what settings you use to get those light curves is needs to be standardized. And so that's why I was asking that question. So either I could give you a light curve myself, or you could make one from a series of FITS images that I send you, and then you put this into a database or a catalog somewhere where everybody can access it on the forum.
Yeah, exactly. That's how it works. Yeah,
okay.
I mean, for sure. I mean, what you said is totally true. Of course, I mean, our idea was, for example, for D and K type stars, which I mean, the duration of the transits around these stars are really long. I mean, a transit of an exoplanet around a G type star lasts for 5 hours or something like that. So we are observing just 4 hours in a row. But the good thing, the good aspect about searching, for example, M type stars, the small ones, is that we believe that we need small observation sessions. For example, for Gliese 5436, the duration of a hypothetical transit was around 3 hours. So that was a good idea, because our observatories are observing 4 hours. So
right.
if there is a transit, it's like in any of them would able to catch the transit, just one observatory, or maybe half of the transit. So the idea was, even for the first detection and for the second one, by detecting just half of the transit would be enough for us. We would need the full detection for the third transit for the confirmation.
Right.
But what you said is totally true. I mean, it's like, if we want to target G and K type stars, we would probably need to standardize everything much more. And actually, for this, we finished the first campaign a few weeks ago, and for the second campaign, we will probably standardize everything a little bit more. All of them the same filter, all of them, the same, a little bit more at that aspect as well. But
okay, all right. Well, so good. All right. I've been reading the chat, and let's see what we got. A couple questions here. So ZooTube, sorry about that. I'm the one that that put you in timeout, but you looked like you were getting argumentative, so I did that. My apologies if you weren't. Superluminal is asking, does that mean it's not possible to detect exoplanets around variable stars? No, that's not. It's absolutely possible to find exoplanets around variable stars, but it adds a layer of complication that I think that you guys don't want to deal with, right, Alberto? I mean, this is a variable star can have planets around it. There's nothing that says it won't, but with the kind of photometry that he's trying to assimilate, it's better, I think, if the stars are more stable. Certainly with M-class dwarfs, you're not going to get a lot of, well, it depends. You might get flaring, but I think the ones you're looking at aren't necessarily flaring stars. So is that right? Am I right in saying that, Alberto, that you're looking for a set of data that is as easy and is not as least complicated as possible to take?
Yeah, exactly. I mean, I think I'm not sure which. I think the list of 10 stars. I think most of them, all of them are not variable. I think, and actually, for example, list 436 is it's kind of a tricky star. Actually, one of the observatories involved told me, "Oh, I think that the star makes a really strange light curves. I think it might be variable because, yeah, I guess that some stars are variable, and we don't. I mean, science don't know yet. We don't know yet that they are variable. But for the case of list, for example, 436, I think it's not variable. But yeah, one of the observatories reported that the star was behaving really strange. And it's true. I mean, when I have been like looking all the data of the observatories, it's a difficult star. So yeah, we try to focus on those stars that are simple, without flares, not variable, and as well, M-type stars are the best ones for us because, of course, the deepness of the transit is going to be much more visible for us of a transit. I mean, around an M-type star. So the deep of the transit is going to be much steep, and also about the time, it's going to take us much less time to find that transit.
Okay, good. Let's see. There was a question about the light curve I showed, and I'm trying to find it. Let's see. What is the? Oh, Dan Helberg is asking, what's the minimum amount dollar-wise that an amateur would need to pay? I'll take this partly because I know what Alberto's trying to do, and I was and remember when we did the Panoptis project in with Keck, they were saying they could help you set up a dual Canon system with a couple of 200 millimeter lenses for $5,000, right? Was what they had projected the cost to be. But then they had added a lot of very nice machine stuff. You could make it for a lot less. I think you can make that for about half as much. In fact, I'm going to try and do that at some point. Because I want to join that project and use that. Have them control the camera to get the light curves that they need. But I mean, if you're looking at the magnitude 15 stars that they're kind of saying is the limit of what you can observe with this telescope, an 8-inch telescope, and you could you don't need to really. I don't think you need to really worry about automating this too much. Let's say you got a C8 or a 8-inch Dobsonian even, and you did some shorter exposure images. Let's say you took, I don't know, 500 10-second images or whatever, and you co-added them up. After processing them, you would end up with a signal that you could then get photometry from. And so I'm going to go out on a limb and say you could probably do this halfway decently, depending on the camera that you purchase, for a couple thousand. Which I know sounds like a lot. Everybody's like, $2,000, I don't have that kind of money. Well, it's not. When you look at other hobbies that are out there, this was something that was pointed out to me by Dustin when we did a podcast on this. Whether you get into riding motorcycles or looking at photography of any kind, or most hobbies out there, the dollar entry is pretty high. And so amateur astronomy, all things considered, is actually in the lower part of the curve, I think. You can get a really good optical telescope, 8 inches, and for under $1,000. And so I think that while it is expensive, I'm not going to try and tell you that $1,000 isn't a lot of money. It is, but compared to a lot of other things that we get involved in. My laptop was $1,000. I have computer equipment. I have video cards that cost $1,500. So all of this stuff adds up with just computing power, gaming systems. A gaming system can with GPUs in it can cost quite a bit of money as well. So I know it's a lot of money, but in the scheme of things, it's not so much, I think. That's my opinion. So, yes, you need a camera. Yes, you need you need an 8-inch or so telescope to do this work. But you can also use this for a lot of other stuff as well. And I don't know. It's all a matter of priorities and what you can do. So, that's my thoughts on it, Dan. I know that it's probably That's more than most people have, but that's my opinion on it anyway. Question. Oh, here it is. Harambe's ghost. Isn't the scatter from ground-based amateur observations too great to be useful? That's a great point, and that's what I was getting to with the calibration issue. So, what's your comment on that, Alberto?
All right. Too great in terms of like
getting consistent results, error bars, right? I mean, the error analysis on this needs to be pretty robust, I think. When somebody gives you either a light curve or a series of images for you to make a light curve from, you're going to have to do some error analysis on this. In other words, how good is the data? How do you deal with that?
Well, yes. I mean, right now, it's like we are not combining the data. We are analyzing the data separately. We are not combining any data. So more or less, each observatory is analyzing its own data because the type of transits we are searching for are really we expect them to be really short. So considering that the observatories are observing for many hours, we believe that for M-type stars, it's not necessary so far to combine any data. But yeah, if we need to combine, for example, we have in the list many G and K-type stars, and for those, we will probably need to combine the data. So exactly, we will need to standardize many things. I have here the list of things that we have like to standardize, but yeah, something, for example, about the filter we use, for example. Also for example, well, let me check because I don't remember what other, but yeah, we will have to standardize everything to be able to spot a potential light curve. Yes, of course, that will be really difficult, of course.
Right, and I think it's important that you do keep all of the observations separate. Here, when you mentioned AVSO before, the American Association of Variable Star Observers, they were one of the first citizen science projects. They've been around since forever. I think the 60s, maybe 70s at the latest. I actually participated in those, and they relied on actual eyeballs looking through a eyepiece that you wrote down what you thought the magnitude was of a variable star, and obviously that is got huge amounts of variation in what a person might think a brightness of a star is. This wasn't done with cameras. This was done by an eyeball and somebody writing down what they thought the magnitude of that star was. And then they would send it in. We'd write it down in a little tabular chart and send it into AVSO, who would then compile it among all the other observations. And what happens as a pattern starts to emerge? You do get this standard deviation of all of the different observations that come in, and presumably they have error bars associated with them, so you know the confidence of these observations as well. And then you can combine those using a lot of statistical analysis on these data points to get a mean or a standard, whatever it is you're trying to get from the light curve itself, and reach your result. Now, as an example, let me put this back up again. This is the light curve that Alberto sent me. He said he got this from a paper. Now, look at all those black dots, right? Those black dots are an observation. And, imagine getting, a bunch of amateurs sending in stuff that goes into the database might have a huge scatter on it. And what I can't tell from this graph is you can see that the blue on there are error bars, and so somebody knows something about the quality of this data, and then they drew that red line based on it. So you're right about variations needing to be accounted for, but imagine that you're at an observatory and you send in an observation. Hang on, I'm pushing too many buttons. And you send in an observation, and your observation, everybody else is getting these nice little tight light curves or little data stream points of magnitudes, and yours is way up here or way down there. Well, obviously there's something going on with that observation. So if it's way off, then you assign some sigma deviation to it, and you either include it in the resulting curve, or you get rid of it. And you might want to re-examine your equipment or your calibration procedures or whatever it is to make sure that you get something a little more like what everybody else is getting. Which brings me to my next question, Alberto. If you said there's a forum where people can access this, can discuss things, Can I see my data as compared to everybody else's? Is there some way to query a database somewhere to see the data, or no?
Yes, I mean everybody has access to others' data, so yeah,
Okay.
you can check. But yeah, you have to compare it by yourself. But yeah, the access is granted. Yeah, you can
Oh,
have
well,
access.
that sounds really cool. All right. So let me see if there's any other questions here.
Mm.
They're talking about cloud cities for some reason. Uh, uh, let's see. Superluminal is asking, what is a good first target for detecting a known exoplanet? For example, if someone has just started out in astrophotography, Andromeda would be a good start. It's big, bright, and well known. That's a good question. So, what would you recommend to somebody on your list of stars that you want to get data for? Where should they start?
All right.
What star would you tell them to start with?
To find potential habitable exoplanets, or
Just
to
to
brag.
participate, to give you data, observational data.
All
What?
right, all right. Well, our next target, for example, is going to be, well, I mean, yeah, it depends on the equipment. But for example, yeah, at least 436 was an easy one because the magnitude was only 10.7.
Say it again,
Uh,
please. You went really
yeah,
fast.
the magnitude of at least 436 was really good,
Gliese 426.
really
Okay.
really low. But well, we already did one. The next one we will be doing what is going to be probably at least 12, 14, which has a magnitude a little bit higher. It's almost 15. I'm pretty sure that some of the observatories are able to get good data with of stars with a magnitude even higher than that. I'm not sure because I never have had access to those big telescopes, but I'm pretty sure some of them are even half meters. So I'm sure that they can do better. But
But
yeah,
it sounds like you're going to help them, though, right? I mean, if someone gets in contact with you, you're going to tell them what to start with, and you're going. It sounds like you're going to help get them started. They're not just going to be on their own, right?
yes, more or less. Yeah, I'm trying. I'm trying to find a star that most of observatories can see, because that's another issue. That some of the observatories, for example, some of the observatories are in Chile, or another one is in South Africa. So yeah, sometimes when a star is visible for some observatories, it's not visible. It depends on the time depends on the month. So yeah, I try to find a star that it's visible to as many as observatories to many observatories as possible.
Okay.
And also, I started. Well, for example, I had an issue with. I had to the first star that I was going to choose was HD 189733, because one of the observatories had he didn't have a telescope. He had just a telephoto lens. So the first star that I was going to choose was a one with a really low magnitude. But he wasn't able to gather data, good data. So finally, that's why I chose another one. That was so. Yeah, that's the thing, that maybe an an 8-inch telescope, it's not enough to gather data for a 15 magnitude star. I'm not sure. It's a little bit
It
maybe on the
depends.
limit.
I mean, yeah, it depends on a lot of things, Alberto. You can't,
Yeah,
but I get what you're trying to do. You want to try to give people an idea of who can get involved, and really, almost everybody can. What you're
yeah,
going to get and what you're going to be able to observe will depend on the size of your telescope, where you are on the planet, what kind of seeing you've got. That'll matter a lot too. There's plenty of times when you might go a little bit deeper than you thought. By the way, when he says a low magnitude, that actually means bright, because in in astronomy, it's a negative scale and it's a logarithmic scale. So the magnitude scale is really weird. -6 is way, way, way brighter than -15. Okay. In fact, I think -6 is the magnitude limit of your eye. And so that sort of gives you an idea of what the magnitude scale is. No end of confusing. And it's based on back in the days of the observers. Just eyeball observers. The eyeball response is not linear like a CCD is, and so it tends to be more of a logarithmic response. Film was also logarithmic and not linear image response. Hans Milling is asking, how do you calibrate the different telescopes and equipment to be sure they measure the same brightness? As they are scattered all over the world, they cannot see the same stars at the same time. Yeah, that's what we were just talking about. So you do your basic calibration on the system, right? And you're obviously going to write down the date, the time, the location of where you are, things like that. And
Yeah.
then the photometry can either be done on your own software using your own set of like DS9 keeps coming to mind because that's what astronomers at the
Yeah.
institute use to get photometry off of Hubble images, and you can either use that, report those numbers, or send in FITS data, and Alberto will run it himself on this. But really, there's going to be variation. There's just no way around
Yeah,
it.
of
Not with
course.
a system
Even
like
if
this.
Yeah, exactly. Even if you use the same telescope and you take observations at a different time of the day, there's going to be there are going to be variations. So it's like really difficult. So yeah, we prefer not to combine any data yet. But yeah, that's really difficult. Yeah. What I was going to say before is like, for example, the number of data points per minute. That's something that we will have to standardize if we want to target G or K type stars. The filter, the comparison stars, more or less until now each observatory decided to choose the comparison star that they wanted. But if we want to combine the data, all of them will have to have the same comparison stars. There's a selection of things that all of them will have to do.
You sounds like you're pretty good. You're going to be pretty busy with this, aren't you?
Yeah, it's difficult. Yeah,
Okay.
that's
Um,
true.
let's see. Michael Aitken. Hello, I'm an AVSO guy. Welcome. Good. I'm glad to see you. Are you still active in AVSO? I haven't done it since I was in high school. I did it as a physics. I'm not a physics. A science fair project when I was in high school, and I didn't really get back to it after that. To be honest, I didn't. I lost track. I lost access to telescopes and couldn't do it. Let's see. Is there overlap between the observatories? This is from Mad End. To find glitches in local weather phenomena like clouds and filter them out. Well, I think that's your goal, right? You want as many people observing this at one time as possible. Do you want me to reread it? The question. He goes, is there overlap between observatories to find glitches in local weather phenomena like clouds and filter them out? So let's say two observatories are looking at one star. It's a little bit cloudy in South Africa, but not so bad in Europe. Uh, can can you like combine them in a way that you get one observation, or do you just throw out South Africa's?
Yeah, well, yeah, that's a difficult thing because yeah, sometimes some of the observatories tell me, okay, I'm going to have bad weather for tonight, and I have to find another observatory near that area. That well, not near that area because that area will have bad weather, but I have to find another observatory in that time zone that has good weather and is able. So sometimes I have to change. Yeah, exactly. I have to change the schedule depending on the weather, more or less. Yeah, that's true. But yeah, most of the observatories have good weather, so that's I didn't have to change too much about that. But yeah, sometimes the change is on the time. I mean, every day, instantaneously. Yeah, yeah, yeah.
Okay. Michael Aitken runs a 24-inch plane wave. Wow, that is a killer telescope. That is a killer telescope, man. You know, messing around. So that, yeah, you could take some data, man. You could take some data. You let's see. You need to get some dark skies from Mag 15 with an 8-inch. That's from Superluminal. So yeah, that's another problem is light pollution. Um, let's see. And AVSO, this is also from Michael Aitken. And AVSO has call of action time sensitive observations. Call of action for time sensitive observations. Yes. Oh, that's cool. Um, let's see. There's a Discord link. Thank you, Peter. Uh, okay, I missed everything and still foggy. Yes, very much active. You can use my observatory if you like. Thank you, man. We're all going to Michael's house. Yes, if you guys have never seen plane wave instruments, they are the bomb as far as telescopes go. They make meter class instruments now, meter class that you can buy and take home yourself. Now, I'm not saying we're going to afford those because we can't, but they're definitely schools and universities, observatories around the world buy their stuff, but you can too. I mean, I saw them at NEAF. And you can get these really beautifully made instruments, and of course OPT has their their remote observatories have a plane wave on them as well. So those are really nice. Um, let's see. Superluminal. I may be lucky enough to own a 14-inch in a few years. Hey man, whatever you got is you. I know you're working with some good stuff that you've got. You've taken some good images. I've seen them. So well done. And all right. Well, is there anything else that you want people to know? Because we're coming up on. We're running out of time here. I've put a link, like I said, in the description box of the website. There's a video to watch. There's a way to get a hold of Alberto to let him know you want to get involved. Anything else you want people to know?
Well, not really. I mean, we're especially interested in finding observatories in Hawaii, for example. Also in well, yeah, East U.S. That would be ideal. Also Texas, that area. We have many observatories there, but yeah, more of them would be nice. Also in Australia, we need, because there is an area of the world with very bad weather, I believe. I mean, from yeah, we have one telescope in one observatory in Abu Dhabi, and then until Australia, you have actually bad. Well, we have one in China. It's in the desert because. In general, we struggle with the weather. That's one of the main issues, or the
Well,
main issues with this. So we would need more observatories in Australia. We only have 2 observatories from Australia. So it would be great to find observatories in Australia and also Hawaii.
well, I'm hopefully going to set up something here in Florida in the next year or so, and I would be definitely interested in providing some observations. So that's the eastern U.S., but I'm also at sea level, and I haven't had a clear night since June, I think, that I could do any decent observing with. It's terrible here in the summer, so I get what your issue with the weather. That's everybody's bane of existence, and of course Hawaii would be great, but that's where all the professional observatories are. There are amateurs in Hawaii though, so maybe there's somebody here watching in Hawaii that can participate and provide some observations. If you're in anywhere along the longitude of Texas, you could also be in Colorado and Oklahoma, Wyoming, and Montana. So that would be a really good slice of the planet to participate in, it sounds like, as well. But yeah, I can see how getting all bunched up is is a problem. I mean, you got population centers for one thing. Everybody lives in places like Europe and the northeastern United States or whatever it is, California, Arizona, whatever. And those typically have really high active amateur astronomy communities. So you're going to get a lot of people bunched in those areas. Or maybe not so much, in other areas of the world, like Indonesia.
Right now we are 25 observatories, but yeah, we would need maybe to reach 100%. We would need maybe 30, around 30 observatories, I think. Also in Chile, we have one in Chile, but we would probably need more in Chile. It's a good area.
Yeah. Okay, so before I go, I just need to find Kev G's question. Apparently there's one. Oh, there it is. So this is Galaxia pointed it out. Thanks for letting me know. Is there any new technology available that can detect atmospheres, or do we have to wait for JWST? Yeah, we got to wait for JWST. And you think photometry is bad, right? This measuring a dip of something that is 1/1000th of the brightness of the star, measuring this variation. I mean, that's what we're talking about here. Try looking at that atmosphere with a spectrograph. So no, and in fact, that really can't even be done very well from the ground, unless you're in a really pristine spots on Earth. So space telescopes have to do it. And you also need resolution. You need things where you can directly image the exoplanet itself. So what you need is something that's big enough, like the James Webb Space Telescope, that can look at a exoplanet that's off to the side, and as well as it's passing through the transit, so that it can see the light going through that atmosphere and measure the spectra. So no, you're not going to be able to do that with amateur equipment anytime soon, and certainly not from the ground. So yeah, we need to wait for JWST. That's why everybody's excited about it. I'm still excited about it, even if it is a real pain in the butt to be having to put up with NASA and Northrop Grumman. But anyway, Raj wants to know if I'll be looking to have access to the data from JWST. Sure. Yeah. Yeah. In fact, it's going to be just like Hubble. I mean, most data are archived, or I'm sorry, embargoed on Hubble for about a year, unless otherwise stated. Like if it's done with director discretionary time, which is, that's just where the director of the Space Telescope Science Institute says this is my time. I'm going to give it to people to use in whatever way I see fit. That's not embargoed for a year. But the reason they do that is so that these astronomers, who in many cases paid a lot of money to get access to these telescopes, not so much Hubble, but other places. With Hubble, they actually pay you to observe. But they give these astronomers a chance to write their papers, do their science, without somebody else doing it first. And so it just kind of gives them a period to get their papers written. And then it becomes available to everybody. And you can recreate that paper's data if you want to, or write your own paper on the data. It's not so critical that you get this stuff as it comes hot off the press, in my opinion. Some of the best discoveries are still being done using Kepler data that was taken, 10 years ago. So it's still, and this stuff is all going to be available on the MAST archive, the Mikulski Archive for Space Telescope, Mikulski Archive for Space Telescopes. That's where Hubble data is. That's where Kepler data is. That's where test data are going. That's where Pan-STARRS data is, and a bunch of other places, and that's where JWST data is going to go. So yeah, I'm looking to get access to it.